Alright, let's go ahead and talk about 2.2, spanning trees and enumeration. So in this section, we're going to continue down our study of trees and a couple of its properties, but mainly it's going to be a focus of one particular type of algorithm. So to start us off for today, we're going to start with a named theorem. So theorem 2.2.1, and this theorem will actually have its own name. This is called a Cayley's formula from 1889. If I have a set S of natural numbers, so for example 1, 2, 3, 1, 2, 3 all the way up to 10, of size n, then there exist n to the n minus 2 trees with that given vertex set S. In other words, if I have n vertices that are labeled, then I know that there exist n to n minus 2 distinctly labeled trees. So if I look at 3 vertices, for example, then if I have 3 labeled vertices, there should exist 3 to the 3 minus 2, or just 3 to the 1 power, trees on that given set of vertices. So for this case, we can prove it pretty quickly, actually. Here I have 3 vertices, and I may ask, how many different trees can I make from this graph? Or from these 3 vertices, to be exact. So my first thing about a tree is, remember, a tree must be connected. So my vertices 1, 2, and 3 must be connected in some type of way, but I still cannot contain a cycle subgraph. So one way I may connect this graph is just by drawing my edges from 1. Another way that I might draw this graph is if I draw it from 2, and then my third option might be drawing it from 3. I can see from these graphs here, I cannot draw any more edges, otherwise I am forced to have a cycle. The other thing I want you to notice here is that yes, these 3 graphs are isomorphic to each other. These are essentially the same graph, but just labeled in a different way. So here, Cayley's formula, we're considering graphs that may be isomorphic but labeled differently to be their own type of graph. So we have Cayley's formula. And the way that they actually prove this theorem is through a very nice algorithm. So to introduce this algorithm, we're going to start by talking about this thing called the proofer code of a tree. So for our next theorem, we're going to talk about algorithmic production of a tree's proofer code. But first off, what is a proofer code? So if I have a labeled tree T, so I have some tree T, and I labeled each of its vertices, let's just say for convenience, 1 to how many ever vertices there are. The proofer code is a unique number sequence that's associated to that tree. So this is an algorithm that we'll be working with, and just with any algorithm, we need an output, some iterations, and then an output. So our input here will be a tree T with whatever vertex set, such that the vertices are labeled from 1 to however many, with at least 2 vertices. So the idea behind this algorithm is that I'm going to construct the proofer code by iteratively deleting leaves and identifying leaf neighbors. So our initialization for this algorithm is, suppose I have an empty sequence. That is the sequence where I don't have any entries. This is where I'm starting off with. And again, I want to end with its proofer code. The iteration of this algorithm states that we delete the least remaining leaf and add the neighbor of x of the leaf to S. And then we continue this iteration until my sequence has n minus 2 entries. So in other words, if I have 6 vertices, then I want my proofer code to have 4 entries. So, and then with this output, we should end up with the proofer code of this given tree T. So one thing I want to note again is that this proofer code is uniquely associated with the labeled tree. Meaning, if I have the proofer code, I can draw the tree and vice versa. So this first algorithm is saying, if I have the tree, how do I produce my proofer code? So here again, as usual with a lot of our terms, this was very wordy. Let's go ahead and do an example to see what's actually happening here. So here I have some random tree T that I've drawn. and I want to produce its proofer code. And here we can pretty clearly see that we have 6 vertices. So, since I have 6 vertices, we know that the proofer code has 2 less entries. Or in this case, the proofer code should have 4 entries. So I know that I should be done once I have 4 entries in my sequence. So let's start off with our first iteration. So for iteration number 1, I'm going to look at all of the leaves of my tree. Recall that the leaves are my vertices of degree 1. Or in this case, I can look at the vertices 2, 3, 5, and 6. But I just want to choose the least leaf. Or in this case, the smallest one would be 2. And I'm also going to go ahead and identify its neighbor. Because it's a pendant vertex of degree 1, it only has one neighbor. Or in this case, the vertex 1. Our algorithm states that we should delete the least leaf, in this case 2. So I'm going to go ahead and do that right now. And then looking at its neighbor, I will add its neighbor to my proofer code. So since 1 is the neighbor of 2, add 1 to the end of my code. Thus, the first part of my proofer code starts with a 1. And now I'm just going to rinse and repeat this process over and over again until I have a proofer code with 4 entries. Let's look at iteration number 2. Again, I'm going to look at all of my leaves. In this case, I still have 3, 5, and 6. But I only want to look at the smallest leaf, or the least leaf. In this case, I have 3. And once again, I'll identify its neighbor, which is 4. And then I repeat my process. My algorithm states delete the smallest leaf. So I'm going to go ahead and delete my leaf 3. And then I'm going to record its neighbor into my proofer code. So my neighbor was 4. So I'm going to add 4 to the end of my proofer code. So here I have now 1, 4. So I completed iteration number 2, and I can continue this so forth. Let's go to iteration number 3. Once again, let's identify my smallest leaf. In this case, my leaves are 5 and 6. The smallest leaf should be 5. And its neighbor is 1. So now I'm going to repeat by deleting my least leaf 5. So I'm going to go ahead and delete that here. And then record the neighbor. The neighbor here is 1, so I add that to the end of my sequence. So before I had 1, 4, now I have 1, 4, 1. I added this extra entry to the end of my sequence. Now let's move forward. Let's see if we can continue this until we have 4 total entries. So far we have 3 entries. We just need 1 more, and then we have our proofer code. So for iteration number 4, let's look at our leaves here. My leaves of my new graph are 1 and 6. If I compare these two, 1 is my smaller leaf, and the neighbor of that leaf is 4. So my algorithm says delete the leaf 1, and then add that neighbor, in this case 4, to my sequence. So in this case, I have the sequence 1, 4, 1, 4. And now this tells me that I can now terminate my algorithm. I have a proofer code or a sequence with 4 entries. So since I have 2 less entries than my total number of vertices, so 6 minus 2, I get 4, I know that I can end my algorithm. Thus, this tree that we've been looking at has a unique proofer code of 1, 4, 1, 4. So we have this here. So now with this algorithm, if I ever give you any labeled tree, you are able to produce its proofer code by repeating the iterations of our algorithm. So again, we had a tree, we produced the proofer code. But what if we want to go in the reverse direction? What if I have the proofer code and then I want to produce or draw the tree that correlates to that given proofer code? So we're going to introduce our second algorithm, which technically is the same algorithm, but just in the reverse direction. So theorem 2.2.3, drawing a tree based off its proofer code. So here the input would be, you would input the proofer code that's given, and we're assuming that I have at least 2 entries in my proofer code. My starting step or initialization or setup is, let's let L be the set 1 to t plus 2. So if my proofer code had, for example, 8 entries, the set L will be 1, 2, 3, all the way up to 10. And then the proofer code will keep it the same in our initial step. And then my number of edges will be empty. My iteration says, and this is going to be very wordy, you're going to see what I mean by this a little bit more clearly when we look at the example. If my set L only has 2 entries, add the edge between the remaining 2 values of L to E of t. If L has more than 2 entries, I'm going to look for the first entry of L that does not belong to S and the first entry of S. Whenever I find those 2, I'm going to add that edge to my edge set. After I add that edge, I can go ahead and delete the first entry from S and whatever that entry from L was. And I continue this until my tree, T, is connected. So let's go ahead and do an example with this. Oh, and here the output, again, should be our tree T that has this exact proofer code. So let's go ahead and look at an example. Draw the labeled tree T where proofer code S is equal to 1, 4, 1, 4. So if I look at this proofer code, there are 4 entries, and then there should be 4 plus 2 vertices, or in this case, I have 6 vertices. So let's go ahead and draw it. I have 6 vertices, and I labeled them 1 to 6. Based off my algorithm, my initialization step is L is in numbers 1 to 6, so 2 more than the total number of entries, and S was already given. And right now I have no edges in my graph. If I want to follow my algorithm, iteration 1 says I look at L and S. Within L, I search for the first number that is not in S, and I connect it to the first entry of S. So if I look at L, I have 1, 2, 3, 4, 5, 6. Starting from left to right, I want to go ahead and see what is the first entry that is not in S. So 1 is definitely in S. Next one, 2. 2 does not appear to be a part of S. So I'm going to go ahead and circle that for us. And then the first entry of S is 1. So I've chosen 2 numbers. From L, I'm always choosing the one that does not belong to S. And for my second one, I'm just choosing the first entry. My algorithm says add an edge between the 2. Or in this case, let's add an edge between 1 and 2, like I've done here. And then I can delete these 2 entries from their respective sequence. So in this case, I'm going to delete 2 from this sequence L and 1 from this sequence S. So L will now be 1, 3, 4, 5, 6, and S is now 1 number shorter. I have 4, 1, 4. Now we can go ahead and continue with iteration 2. So here I just have what we got from our first iteration, our new set L in sequence S. And I pretty much rinse and repeat over and over again. Again, I'm going to look at L and what's the first number that's not in S. If we compare the 2, we can see our first number of L that is not in S is 3. And then the first entry of S is 4. By my algorithm, I add an edge between 3 and 4, like what I have here. And then I delete those respective entries. If I delete 3, I get 1, 4, 5, 6. if I delete 4, the first entry only, I get 1, 4. So I've finished my second iteration. Continuing from here, let's do iteration number 3. Once again, I'm going to copy down this data from iteration 2 on top. I have 1, 4, 5, 6, and 1, 4. And I repeat my process. I look at L. What's the first number that we see that is not an S? If I look at this, I should see the number 5 does not belong to S. And the first entry of S is 1. Thus, I'm going to go ahead and add an edge between the two, giving me the edge 1, 5, like what I've drawn here. And then I delete both numbers from their respective sequence. So from L, I should be left with 1, 4, 6. And S, I'll just have the entry 4. And we're going to keep on continuing this until L only has 2 entries left. So we should be able to do this in one more complete iteration at least. So here, the data from iteration 3, we had 1, 4, 6, and S was just the entry 4. I'm going to go down and look at L and see what's the first number that does not belong to S. And I see that we have 1 here. And then the first entry of S, in this case, has to be 4. So I draw an edge between 1 and 4. So here, if I draw the edge, I have this new picture. And then I delete these 2 values, leaving me with L is 4, 6, and now S is the empty sequence. I should be able to do one more quick step here to complete my algorithm. So for our last iteration, notice here that L only has 2 entries. Recall that our algorithm said if L has 2 entries, I can just add an edge between the 2 remaining vertices. Or in this case, as you just saw, I added an edge between 4 and 6. So since L has size 2, add an edge between the last 2 values. Once I do that, I can finally terminate because my graph is now connected. I can see here that all of my vertices are connected to each other, and I'm still acyclic. Thus, I now terminate. One thing I want you to notice here is this graph should look a little bit familiar. It's shaped a little bit differently. But my choice of the proofer code here, this was the exact same proofer code that we had from the previous example. If I look at this, I can see that this is actually the same graph, or at least isomorphic to the same graph that we had before. So again, this is why I said that technically this is sort of the same algorithm, just going in different directions. So this is our coverage of the proofer code. And in notes, there is one small little definition and proposition, I believe, talking about contraction. Make sure that you do take a look at that example. We won't talk too much about it for this section, but it is a nice and handy thing to know. Besides that, I'll see you for the next video.